Today we will start Stiffener design. Before starting, let me remind you that this portion is little difficult and little confusing to follow. So please stay with me. So first of all, why do we need a bearing stiffener? So here I drew a a profile or cross section of a beam. So there is a concentrated load here, and that will produce a concentrated load in the support. So there is concentrated load at the end of the beam and here also. Now we should check the wave capacity, like wave yielding, wave crippling, wave side sway buckling. Okay, let me write here. Wave yielding, wave crippling, and wave side sway buckling. These are the three check we will have to check for a wave. There are three other checks, that is for plate. So if we use a plate here or below the load, we should check the bearing and bending in plate, and we should also check the support capacity. These are the 6 checks we should do if there is a concentrated load. Now if we provide a bearing stiffener, we do not need to check all these three. So what is bearing stiffener? What we do, we insert a plate here or here. So we insert plate just below or above the concentrated load. Now how do we insert the plate? So we insert plate here and here, and then weld it here. Weld it here. We also sometimes we weld here, but that is not part of the strength. Our main strength is here. So why we do this? So what we are checking here, this is all about wave. So wave yielding, wave crippling, wave side sway buckling. So if our wave thickness is very small, we need to increase its capacity. How? What we are doing here, we are inserting two plates. Now these two plates will work with the wave. Now the whole part will work as a beam. Sorry, as a column. So here you can see this is my concentrated load, and this portion will be my column. Now this portion, it has my wave, it has the plate on both side, and some part of the wave in this way we will also work as a column. So that is something to understand, that by providing stiffener both side of my section, I am increasing the cross section of the wave. So this way and also that way longitudinally. So we will see it. Now how to find the capacity of a stiffener? So this is the equation. If we know that for column the strength depends on KL by R ratio, which is slenderness ratio, KL by R. So if KL by R is less than or equal to 25, we can find the capacity of the stiffener or of this section using this equation phi Fy Ag. Again, Ag means the gross area, that is the wave and the plate combining everything, and Fy is the yield stress, and phi is obviously 0.9, the strength reduction factor. So this way we can find the capacity of a stiffened section or stiffener. Now if it is more than 25, what will happen? Whatever we learn in chapter 5, the normal column table, we can use that. So whatever the ratio is, then depending on the ratio, the equation valid for a normal uniaxial column, we will use that. Another criteria is the is called bearing strength of column. Now what is this? P is the strength reduction factor 1.8 Fy APB, projected area for bearing. PB means P means projected, B means bearing. What is that? If I go to that figure again, so that means in this figure, so there is a curve part here. So here this portion and this portion might fail in bearing. So that is the area. That means we will take this length, this width, and times two sides. So that is the projected area for bearing. But your book says that criteria rarely controls. Rarely controls. That is not so important. This is more important. So, but we will. It's very easy to calculate. Uh, Again, before going there, let me revise one thing. How to calculate this length? This length is simply whatever the plate size. Say this size is I don't know, say 3 inch, minus this curve part is k1. That means this curve part here to here is k1. So make sure that you know what is k1. So the projected area can be found. So two sides, so 2. Then if this is 3, it may not be 3, I'm just assume 3. Then k1 times the plate thickness, whatever the plate thickness, say t, whatever the plate, there is no standard name, say p means plate, the plate we are inserting here. So this is how you can calculate the projected area for that stiffener. So a p b. Okay, that is not our discussion. Even that there is also a discussion. So our main discussion, we will go now. Say here. So we saw how to calculate the strength. Again, to find this, we need KL by R. K, what is K? K, your book gave us. K is the depends on the support type. For stiffener, we use 0.75. So K is known, 0.75, universal for stiffener. What is L? L is our length of the column, right? We know that length. Now what is our length here? Our length here should be this length. Length here should be this length. Now again, it is not, we should deduct that curve portion here and curve portion here. That is that effective length. How can we calculate it? Total depth. So how can we? Total depth is d. Total means from outside to outside. Then we have to deduct this portion, both sides, this portion. What is this portion? If we can remember, that is k. So we can find now. Then twice k. Twice k. Why? Because one side k here, other side k here. So from d minus twice k is our the length of the column. Now k1 whatever, you can find it from the AISC manual chapter 1. That is not a problem. Okay, so let us, so we found, we know what is K, we know what is L, the length of the column or stiffener, very small length. What is R? Radius of gyration. That is the challenging part for column, stiffener design. What is R? Let me write it down. R is square root I by A. What is I? Moment of inertia of my combined column here or here, the combined moment of inertia, and A is also the combined area here and here. That is the challenging part for stiffener design. So we will go to see here or something else. I will tell it later. Okay, let me tell it, clarify here. What is the difference between a stiffener here and here? Here if I draw the plan view means if I cut here and show you here, that will look like, so my section is this, and I have the wave here. This is the end of the beam, and I am inserting a plate here, and some part of the wave will work as a column. So this will be my column. Now this distance is 12 tw. The difference between here is when we use this, that will be 25 tw. That means this value if I use for intermediate stiffener, that will be 25, not 12. For the end, this is for end. For end, this distance is 12 tw. What is this distance? That means if I insert two plate, one plate here, another plate here, then and weld with the web. Some part of the web will work as a column. That means some part of the web will contribute to the strength of this column. So this is a column. This is like a x section column and it's long. X type section and it is long. The difference between again here and here is just this 12. 12 is for in column, sorry, in stiffener, it is inside 25. So do not forget it, inside this will be 25. For this case it is 12. That is the only difference. Everything else will same. Now we will see, now we have to find the moment of inertia and I of this section to find our R. That is something, it's challenging. Now is it challenging? Can you find the moment of inertia of a section, composite section like this? Very simple. Okay, I will sketch a clear one to show to see better. But very, I know that you know it. How to find it? First, this is our axis. Or let's take a new page. So if I draw a bigger one, so bigger one, and this is my combined axis. What we will do? So this plate and this plate, they are same size plate. So whatever this distance is, so we will find first b is cubed by 12 and then transfer it to the composite section. And how to do it? We will do a1 d1 square, which a1 say is. Then what we will do? We'll multiply by 2. Why 2? Because this one and this one both are similar or same plate. We should insert both sides same plate. So this okay, right here b1 h1 cube by 12 a1 d square. Now that means these two are covered. Then here we will find it. How to find it here? The centroid of this section, that means this third section wave, is same thing of composite. So here only say what is b1? b1 is this one, h1 is this one. So here b2 is this two. So b2 h2 means here h2 by 12. There is no AD square because we do not need to transfer. Then the combine this and this will be our combined I. So if I sum this, it will be our combined I. What is my combined A? Combined A is mean area of this, and area of this. So that should not be a problem. So hopefully you understood the concept of finding I. Now we will see this using an example. Okay, maybe before that again to revise. Once you find I, once you find A, we can find R. Then depending on KL by R, if it is less than 25, we can find the capacity is A gross area Fy. Then we should check the bearing also. And welding, sometimes we do it, sometimes we do not need it. Welding means, so inside this where we curve here, if we insert a plate, the welding capacity here, but that is a different story. So next we will see an example. I will stop here. In the next video we will start that example.